talk about sequences, say, approaching 5 or approaching their limit value. And so the students have written this down, and then they look up at the board where there's these rows of examples and non-examples that Craig was describing. And we're starting to question the validity of their definition, and they pointed to several of the graphs where they said, well, that doesn't really describe what's going on. And for example, Belinda, who's shown here, points at what was labeled graph A. You see that on the left, and she says, these early points here, they're moving away from 5 now. So we can't really say that this definition works. And they pointed out, both Megan and Belinda pointed to several other graphs where that wasn't the case. For example, a damped oscillation. So I can make sure I press the right button. What we'd like to do is, just to kind of make sure that we're all on the same page, is take that example where the students were using this language of a sequence converging if it approaches the number 5, and get your sense of whether you think that that's an example of the students exhibiting a problem, a problematic issue, an explicit solution, or an implicit solution. Okay, it looks like we're pretty evenly divided there. And actually, so this might be a good point of clarification. So we actually took this as a problem for the students rather than a problematic issue. So I'm just going to back up to that slide. And so what's happening here is the students are looking at their definition, and then they're looking at the graphs, and they're pointing out that there's conflict between what they've written as the definition and what they've written and what they've drawn as a graph of something converging to 5. And so since it's the students explicitly bringing that up as something that's wrong, we call that a problem. And we're reserving the term problematic issue for something that the students are basically unaware of and are not explicitly addressing. So what I would suggest is, if people have questions as we continue to go through some of this, for example, if that's still not quite clear, go ahead and type those in the chat window. And since there's 2 of us, there's only one of us talking at a time, and the other one can try to respond to questions in the chat window if anybody would like further clarification on anything. Okay, so I'm coming back to the definition 2 that they had. Sequence converges to 5 as n approaches infinity, provided the number approaches or is 5 and no other number. And so we are notating that the students viewed that as a problem, and they use the phrase bad early behavior. And what I'm going to illustrate through the following slides is the way that they came to a resolution of that problem by introducing the idea that they called at some point n. And so they're going to introduce the idea of the behavior of the sequence changing at some point. And this is going to be an explicit process. So Megan, for example, after they've pointed out that several graphs have that problem, said, well, what if we were to say after some point n? So we have random stuff going on. She's pointing at all of the graphs they have up on the board that are convergent. And she says, but at some point it does start doing the closer and closer and closer thing. All right, so this some point n is connected to the idea of the behavior of the graph changing to fit the approaching idea that was captured in their definition. And so when they went to revise their definition, they incorporated that idea basically by inserting the phrase at some n into their definition. So you can see what they wrote for definition 3. And we'd like to give you another opportunity to kind of chime in. And looking at this definition, what problematic issues do you notice arising with this definition? Now, again, here, problematic issues are things that the students are not aware of or may not be aware of, since you don't have any further information about what the students were doing, but what potential problematic issues might arise that they're going to need to resolve if they're going to come to precise formal definition. So I'll give you a chance to enter ideas in your chat window. How close does it have to be? All right, so they're saying it becomes closer. Is it just enough to get kind of close, or does it have to get some actual degree of closeness? Let's see, April, that n is actually reached, that this some point n is, there's an actual place. Let's see. Gary, okay, so this is monotone convergence. So this is suggesting that it's maybe perhaps suggesting monotonic behavior. And some versus every, right? Okay, so in some sense, this idea, this n is static, it's fixed, is what I think what JD is pointing out there. Okay, it's Siham, I think I'm pronouncing your name right, pointing out the same thing there. So all excellent ideas, and you're probably faster data analysts than we were. So I'll show you some of the 4 of the things that we recognized as problematic issues that came out of this resolution. So in other words, they solved one problem, came up with this idea of at some point n, but this resolution is going to create new opportunities in the form of problematic issues. So first of all, one thing that I don't think anybody mentioned actually was that they're using this lowercase n in multiple ways. So they've got it as this fixed sum n in one sense, but it's also the subscript on this little a, this a sub n plus 1 there. So it's got to be one thing on the one hand and lots of things on the other. Another issue is they've got they don't really have a strong or precise way of characterizing the terms that they're, yes, notation always is an issue. How do you say everything past this point, right? I mean, the idea of using, say, a little n greater than or equal to a cap n, first of all, they don't even have 2 different types of n's to use. So they have this n plus 1 kind of idea to refer to things later, but that's still, if you take it literally, some n, then n plus 1 is just the next term, not a lot of terms. Our third problematic issue that we identified was exactly what several of you pointed to. It's tied to the place where the sequence is viewed as becoming monotonic. And they did kind of shift this to include the idea of alternating, but only alternating in the sense where it's still getting the difference between the term and the limit is decreasing. So even when they generalize it, they weren't quite thinking the right thing. And then the fourth problematic issue is another thing that several of you pointed out, is that this sum point n is a fixed place. And they actually went up to the board and identified, okay, for this sequence, here's, the sum point n is 5. And at that point 5, and when n is 5, the sequence is going to start becoming closer and closer to 5. Sorry, I used 5 in 2 different ways there. But they would identify that at some point n for each graph. Okay, so this is coming back to the notation that we had, diagram that we had before to indicate that they had a problem, resolved it, came up with this idea of at some point n. And then out of that arose these 4 problematic issues, which I just described. And I'm using these thin black lines to denote where problems or problematic issues came from. So the origin of these 4 problematic issues was actually the solution to another problem. All right, so I'll talk about these 2 as well. Okay, implicit and explicit. So implicit, okay, solutions are explicit if the students were actually talking about it in the context of that problem. So let me go back here. The students generated this solution of at some point n explicitly to deal with the problem of early bad behavior. So that's why we call that an explicit solution. I'm going to show you some other things later where they were talking about things, but they weren't attaching them to a specific problem. Nevertheless, those things that they introduced resolved the problems, even though they weren't trying to. I think that'll become more clear as I talk more. Craig, feel free to type something clarifying in the chat window if you think it would help. Okay, so I'm going to focus now on the two problematic issues of the n being a fixed point and it being the point where it's related to things getting closer or decreasing errors. And what happened was, instead of noticing, so the two students in our study didn't actually notice these issues. That means they remained problematic instead of becoming problems. Instead, they were focusing on some other problem. They were asking this question of how close is close? In fact, this is one of the issues that some of you, or one of the issues that somebody raised, and a potential problematic issue, but this is one that the students actually made explicit. How close do you have to get? And I'm going to show you some discussions in which, in talking about that, they introduce this idea of, well, what that really means is there's some acceptable range, and once you're in that range, then that means you're close enough. And then what's going to happen is they're going to transfer this idea of at some point n to where the sequence enters that acceptable range. And that's going to end up being then an implicit resolution to the problematic issue up here, that n is tied to a place where the errors start decreasing. So they're not thinking about that as a problematic issue, but they transfer the meaning of at some point n due to them resolving a separate problem. Okay, so here's where that happens. They're wrestling with this question of how close is close, and Belinda says, well, it's close as when there's an error, but it's, and Megan jumps in and says, we were doing that stuff before in where our approximation had an error. Remember when we had to find it within 0.0001 or whatever? So she's remembering things that they did in class. Belinda agrees, and Megan says, I guess we can say within a designated margin of error, or designated error bound, because it would vary by what our error bound was for that particular problem or situation. So Megan is suggesting that they incorporate that idea into their definition. And here's a longer quote where Megan is elaborating what she means by that. And you can kind of read the quote if you want. There's the one thing that I want to point out about the structure of this quote, and that's the places where she references this acceptable range. I've highlighted those in red now. So she talks about a range, that distance, that small little range, and a little acceptable range. So one thing that's important to notice about this is that every single one of those references refer to it as a single thing. It's so that the acceptable range to them, and they elaborate this over and over in their conversation, is a single number. Now we recognize this as the thing that's eventually got to become epsilon in the solution. And so it's got to have a for all attached to it, a universal quantification. So it's got to be, multiple things, and in some sense everything positive. But for them, it's just one number.